in this third session of the ISARM2021 conference. So this morning here in Paris, we will discuss transboundary aquifers' contributions to Sustainable Development Goals. And my role here is to introduce you with Mr. Sherman, Mr. Kukurich, who is the director of the International Groundwater Resources Assessment Center. So, Mr. Kukurich, the floor is of you.
Thank you, Paulina. Good morning, good afternoon, good evening, dear colleagues. And, we are now starting a new session at ISARM conference session, which is dedicated to contribution of transboundary aquifers to SDGs. And we have quite a number of interesting presentations these sessions, and we will go through all these valuable contributions and hopefully then have a lively discussion before we close session 1:45. So my role here is just to introduce speakers and later on to lead a bit discussion. So let me start with our first speaker, and it's Charalampos from Thessaloniki. I think we know each other, and so title of your presentation is updating the ISARM Balkans Transboundary Aquifers Inventory, a tool for shared groundwater management. Well, personally, I'm very curious about your presentation because of a lot of work in the region. So let's hear your presentation. Charalampos, floor is yours.
Thanks a lot. Can you see my screen?
Yes, just speak up, please.
Yes. Okay. Thank you, Mr. Chairman, for giving me the floor. I'd like to thank you for participating in this first presentation of this session of session 3. Our work is focused on updating the ISARM Balkans Transboundary Aquifer Inventory, a tool for shared groundwater management, and it was conducted by me, Charalampos Koulikaris, Zaganoulis, and Zan Fried. During UNESCO IHP ISARM initial phase 2000-2008, UNESCO Chair INWEB, which is located in Thessaloniki, Aristotle University of Thessaloniki, has contributed to the development of the transboundary aquifers inventories for the southeastern Europe, a region that is broadly known as the Balkan Peninsula or the Balkan region. A few years later, a global environmental facility project, namely Transboundary Water Assessment Program TWAP, and particularly its groundwater component, which was supervised and executed by UNESCO IHP, aimed at providing the description of TBAs with an extent bigger than 5,000 square kilometers, and the identification of the major issues, concern, and hotspots on this TBA system. Our work, our research is a coupling of these two issues. We try to implement this TWAP project indicators methodology on the Balkans area, having as a reference the data that were collected during the INWEB's inventory. On the figure, you can see the area of interest and the numerous TBAs that were identified in 2008. And what is particularly important is that these TBAs are relatively small And but you will see at the next slides that they are very important to the region. So starting with the TWAP implementation methodology, it is based on a system of 10 quantitative indicators and various thresholds that in order to be defined and populated, the sources for data came from structured questionnaires that were used to collect data for each TBA system, and the implementation of a model, of the water gap model, that was used for the computation of all the values that were needed for the subset of indicator for the TBAs that their extent was bigger than 20,000 square kilometers for both current and climate conditions. Here we can see a panorama of these 10 indicators. Indicator 1.1 has to do with mean annual groundwater recharge. Indicator 1.2 reflects the mean annual per capita groundwater recharge. 1.3, the natural background groundwater quality, which means the percentage of the aquifer area where groundwater quality satisfies local drinking water standards. Indicator 2.1 is related with human dependence on groundwater. 3.2 indicator has to do with groundwater pollution, and 4.1 indicator has to do with population density. Indicator 4.2 is related to groundwater development stress. Indicators 5.1 and 5.2 has to do with transboundary legal and institutional frameworks, respectively. And finally, the last indicator, 6.1, has to do with the control of groundwater abstraction. So during this, and a few words about the INWEB TBA's inventory. It was conducted in 2008, and it's freely available on UNESCO site. In 2004, a coordination meeting was held in Thessaloniki, and national experts, scientists, and policymakers from all the Balkan countries were together, and the 47 TBAs were identified, however, without a lot of data attributing the status of these TBAs. Thus, a follow-up second meeting was conducted in 2007, and finally, 65 transboundary aquifers were identified in the area, and with data about the boundaries, also about discrete information were given in this coordination meeting. Going to the results and the implications, we saw that the INWEB's inventory doesn't have a lot of information that we need for populating these TWAP indicators, this set of indicators, because mainly we are lacking of recharge and abstraction data. Water volumes of this recharge and abstraction were not recorded in this inventory. However, there are some indicators that could be populated based on the data that were collected during that period in 2008. And I'm going to demonstrate you in the next slides. Going to indicator 1.1, which has to do with the mean annual groundwater recharge. Recharge data in the inventory were given only for one item. Of course, we had data about annual groundwater resources and precipitation for, let's say, half of the TBAs. So indirect methods maybe could implement for calculating the recharge. However, what we propose is that a new survey, it should be conducted in the area in order to find this type of data. The same for the indicator 1.2, which has to do with the total groundwater recharge divided by the population. We don't have data about the recharge, so we cannot compare. Indicator 1.3 has to do with the percentage of the aquifer area where groundwater natural quality satisfies local drinking water standards. We saw in the inventory that 72 of the TBAs are used for drinking water. So this is a very big percentage. So we can say that we can consider 100% this percentage for this indicator in the cases we have this type of data. Indicator 2.1 has to do with the dependence on groundwater. Groundwater abstractions are provided for 35 national parts of aquifers, which correspond to 26 of the total identified transboundary aquifers. Thus, we need more data that the survey is proposed to be conducted in order to retrieve these abstractions. This figure goes together with indicator 1.3, where we can see that the water in this area is primarily used for drinking purposes, and the correlation between the countries that share a transboundary aquifer, so that almost in all cases the water is primarily used for water drinking purposes. Going on, indicator 3.2 has to do with the groundwater pollution. So specifically the polluted zones as a percentage of total aquifer area. We saw that, as I said before, these TBAs are used for drinking water, so we can consider that the percentage is negligible. Indicator 4.1 has to do with the population overlaid in this area, the stress caused by population. This is an easy task where we can couple census statistics with GIS tools in order to find this figure and populate indicator. Indicator 4.2 has to do with abstractions. We don't have this type of data, so we cannot populate this indicator. Indicators 5.1 and 5.2 has to do with legal and institutional frameworks. In that era, we saw in that period in 2008, very few transboundary aquifers were under a bilateral agreement or treaty, only 10%. So we need more updated data in order to compile this indicator. And the data were even more or less when referred to institutional arrangements. Finally, the indicator 6.1 has to do with the control of groundwater abstractions. Since we don't have data about the water abstractions, we cannot go further and compute this indicator. However, at this point, we should mention that INWEB's inventory was, let's say, the reference point, the start point. Since then, there are some very important initiatives and programs, such as the DICTAS project that was executed and coordinated by IGRAC, where valuable information regarding recharge and abstractions were identified. And one other important issue has to do with the fact that many Balkan countries, such as Greece, Bulgaria, Romania, Slovenia, Croatia, are currently members of the European Union, which means that they implement the Water Framework Directive. So they have data about the groundwater bodies. They have data about the recharge and abstractions. And this figure demonstrates the current status of the groundwater bodies that are located in the boundaries of the Balkan countries. We see on the left-hand figure that regarding the chemical status of these groundwater bodies, most of them have a good chemical status. And the right-hand figure is related with the quantitative status, meaning the abstractions. So we see that in most of the very few cases, very few groundwater bodies are stressed because of over abstractions. So in these cases, we have data, we have figures, numerical data, so we can use them to calculate the TWAP indicator methodology. To conclude, we see that in this area, there are a lot of local aquifers, even with moderate water potential. However, they have a very big importance in the area because they are sources of drinking water. And they cover the water demand for water supply. And moreover, they are subject to strong pressure, especially in summer during agriculture and touristic, because of agriculture and touristic activities. Moreover, even we have data for some of the countries, EU countries of the Balkan area. There are many countries, particularly in the Western Balkans, that they are not still members states of the EU. Thus, what we propose is that the small-scale funding could further foster the retrieval of data in form of questionnaires, and we can see the evolution of these TBA's management together with the data that were produced by DICTA's project and the other projects that were in the area. And of course, the contribution of the WFD, where we have a lot of data for all the countries that are member states of the EU. Thank you a lot for your presentation. I'm looking forward to your questions during the last session.
Many thanks, Charampos, for this overview. We will hopefully have a little bit of discussion about this at the end of the session. And but now I would like to move to next speaker. The next speaker is Christina. Christina is, I see, from IGREC. And Christina is going to tell us something about transboundary cooperation per aquifer and the Sustainable Development Goal Indicator 652. Christina, the floor is yours.
Thank you. Yes, so I will start by briefly going over what the SDG indicator 6.52 is, for those of you who are unfamiliar with it, alongside the reporting and results from the most recent cycle. I'll then introduce the rationale and aim and methodology of this research, followed by some provisional insights and limitations, and concluding with the next steps. So SDG target 6.5 is the implementation of integrated water resource management at all levels. In order to track and measure the progress of this target, countries are asked to report on two separate indicators. The second indicator, 6.5.2, is the proportion of a transboundary basin area with an operational arrangement for water cooperation. And encouragingly, many countries, 129 in fact, reported on this indicator during the second phase in 2020. Countries must report on individual transboundary rivers, lakes, and aquifers they share with neighbours, and state whether each has an operational arrangement for transboundary cooperation covering it. In order to be operational, an arrangement must meet 4 criteria: a joint body, mechanism, or commission for transboundary cooperation, regular formal communication, joint objectives and a common strategy or action plans that are agreed upon by riparian countries. And finally, there must be regular exchange of data and information. The reporting results are then represented as a single percentage per country, calculated as the proportion of a country's transboundary basins covered by an operational arrangement. In 2020, there were 101 country indicators available. However, as you can see by the map in the bottom right-hand corner, these country percentages don't provide an insight into which transboundary basins have operational arrangements and which don't. In order to know this, you'd have to download and read an individual country report. So for example, South Africa reports an indicator value of 45% for transboundary aquifers. Which aquifers are not subject to operational arrangements and which are? The aim of this research was to therefore present the state of transboundary cooperation globally per aquifer rather than per country, in order to highlight which TBAs are subject to operational arrangements and which only partially meet the 4 criteria. In order to do this, we extracted aquifer-specific data from each of the submitted country reports, which are all available online from 2018 and 2020. And we then spatially represented this data. On the map, we use different colors for country aquifer segments to represent what was reported. So, for example, if one country reports that one of their TBAs is covered by an operational arrangement, this portion of the TBA that lies within that country is colored green. If countries report that there's no operational arrangement, this portion of the TBA is colored red. We then have a range of blue colors to reflect arrangements that aren't fully operational, but do meet some of the 4 criteria. When no report was submitted, this is just colored gray. The aquifer delineations we used for the map are those from the 2015 Transboundary Aquifer Map of the World, as these were the shapes available to countries during the reporting rounds. In some cases, countries reported using different aquifer names. However, in most cases, it was possible to link what was being reported to an individual delineation. The map is still undergoing verification, so I'm not going to go into too much specifics about what we're seeing, but I will provide a few examples in order to highlight the power of representing SDG 6.5.2 data in this way. First, looking at the Sheri alluvial aquifer shared between Malawi and Mozambique, which is the aquifer at the bottom of the map there, extracting aquifer-specific data from the country reports, we can see that Malawi reports an operational arrangement over this TBA and is therefore colored in green on the map. However, Mozambique doesn't report at all on this aquifer, whereas it does for others. So why is this? If an operational arrangement does exist, this would be an easy gain for Mozambique to report on it in the next round and increase their overall indicator value. If an operational arrangement doesn't in fact exist, then Malawi is overestimating its indicator value. If we look at the entire USA-Mexico border, Mexico reports operational arrangements for all shared TBAs with the United States of America. The USA reports that there's no such arrangement. What is the reality? And why are there inconsistencies as to whether or not these TBAs are covered by operational arrangements? Finally, Botswana reports an operational arrangement with Zimbabwe over the Eastern Kalahari-Kuru Basin. The Zimbabwe reports that only one of the criteria for an operational arrangement is met. Is there a misunderstanding on what constitutes an operational arrangement in this case? Presenting SDG 6.5 data in this way allows us to not only look at the state of transboundary aquifer cooperation for individual aquifers instead of countries, but it also allows us to pinpoint these cases where countries are reporting different things in order to validate what the real on-the-ground situation is. Other than the visual impacts of presenting aquifer cooperation in this way, we can pull some other insights from the data. Only 12 countries report having a total of 8 aquifer-specific agreements in place. Indeed, most of the cases of transboundary aquifer cooperation are through surface water arrangements, with river basin cooperation in particular being a vessel for transboundary aquifer cooperation. There are 32 cases where some, but not all of the criteria are met for an operational arrangement. In these cases, criteria 1 is the most commonly achieved criteria, with criteria 3 being the least likely to be met. This means that in some cases, joint bodies or commissions do exist, but they don't have an agreed common strategy. In terms of limitations, the data ability for transboundary aquifers means that it can be very difficult for countries to report on the aquifer component of indicator 6.5.2, and this ultimately leads to gaps in our cooperation map. However, even visualizing these gaps can allow for more directed intervention. In some cases, countries are reporting different things for the same transboundary aquifer. This could arise from either a misunderstanding on what is being considered as an operational arrangement, or simply disagreement between countries on what is actually being done on the ground. Another limitation is when countries report on the inclusion of groundwater cooperation under surface water arrangements, it's often unclear just how embedded groundwater cooperation is within these arrangements, or whether it's simply mentioned. So for example, an arrangement might be made to share surface water data within a river basin agreement, but is groundwater data also being shared? Regular meetings might discuss surface water issues, but are groundwater issues also being discussed? In terms of presenting data spatially for SDG 6.5.2, Europe in particular, it presents quite a difficult case study because some countries in the region do report on transboundary aquifers and others are reporting on transboundary groundwater bodies. And it's therefore hard to get a coherent picture of the state of cooperation per aquifer in this region. So to conclude with some next steps for this research, our first task will be to complete the verification of the map and publish this next year. It's then hoped that the map can be a valuable resource for institutions and countries to see where easy progress can be made in terms of increasing cooperation indicator values for 6.5.2 in the next reporting round. Within a wider context, it could also be a tool to visually represent where we need to be investing more time and money to improve aquifer assessment and data availability. We also have some plans to develop a live transboundary aquifer cooperation database, where this data can be easily accessed alongside information on which specific arrangements are being reported on, something that's quite difficult to represent on a map. Finally, often we see the narrative of there only being a handful of transboundary aquifer specific agreements. I've already seen it being said many times at the conference. This is true, but the SDG 6.5.2 data shows that there is more cooperation and data exchange over these TBAs than we often give credit for. With increased financing for data collection and a focus on monitoring and assessment, the scientific baseline for transboundary aquifer cooperation, whether it's through river basin or aquifer-specific arrangements, can be achieved by 2030. Thank you very much for your attention, and I'll be happy to answer any questions at the end of this session.
Many thanks, Christina, for this inspiring presentation. And well, of course, there are a number of questions that I would like to raise, similar with the first presentation. You see that in both cases, for instance, this harmonization with the transboundary groundwater bodies in European Union is one of the challenges for cooperation mapping in case of your presentation, and for the harmonization of technical data in a first presentation of Charalampos. But let us hold these questions for the end of the session. And I would like to move to next presentation. In next presentation, that will be Christoph from Atomic Agency. Are you around? Yes,
I am here.
I see you. Hi.
Can you
How are
see
you?
also?
And not to my surprise, but Christoph is going to talk us about isotopes. And the title of his presentation is Regional Capacities for Isotope-Based Assessments on Transboundary Water Resources in Europe and Central Asia. Christoph, floor is yours.
I cannot hear. Maybe it's muted.
Christoph, we lost you for the moment. Could you just give a sign that you're around? Yes, you are around. I mean, and could you share your screen?
I'm sorry, I already started and I didn't notice. Can you hear me now?
Yes, please, please, just start.
Oh my God, I'm sorry. Okay, I will be.
Oh, it's okay. We are good with time and just relax. Now it's perfect.
It works now? Perfect. So I just said my name, that what I will present, that I'm from the agency, and that I will present this on behalf of this great team here from all the counterparts, as well as my colleague Oliver Kraft, who will be talking after me on his experience in Africa. I am from the International Atomic Energy Agency based in Vienna. Many may know us as the nuclear watchdogs for non-proliferation in the context of safeguards and nuclear weapons. However, we do a lot of other things in the area of nuclear science and technology, including nuclear applications, for example, helping member states to use nuclear applications such as radiotherapy or nuclear medicine for human health, as well as other nuclear applications that are supporting our member states in enhancing the sustainable development. Hence, our motto is Atoms for Peace and Development. And one of these nuclear applications is isotope hydrology. And isotope hydrology is a nuclear technique that uses both stable and radioactive environmental isotopes to trace the movements of water in the hydrological cycle. And the specifics maybe about this is we are not tracking any tracer, but we're tracing the water itself, since we're looking at the isotopes of hydrogen and oxygen. And isotope hydrology looks at how these different isotopes vary. And hence you see also the delta value in this little graph here in different water molecules in different parts of the world or the hydrological cycle. And by doing so, we can really understand where the water, for example, is coming from, where is its source, where does it go to, what is its age, how aquifers are recharged, how old the groundwater is, and therefore I would say invaluable information actually on the sustainable management of water and in particularly shared water resources. So isotope hydrology allows for a rapid understanding of the hydrological system that may require years or decades of monitoring if you would use other techniques. In some cases, it is even a nearly unique tool, and it is also cost effective. And in the region that I'm focusing on is the Europe and Central Asia region. Of course, also there, a better understanding of complex aquifer systems and groundwater, surface water interaction is also indispensable for an effective integrated water management, and particularly under the stress associated with groundwater depletion, its quality, deterioration, pollution, including, for example, of anthropogenic activities as well as climate change. And isotope hydrology is an excellent tool, as I had explained. However, the proficiency as well as the capacity to utilize isotope-based techniques in our region significantly differs among the countries that we're looking at. So to respond to this, we have started a regional project in 2020 that should focus on enhancing evidence-based decision-making in support of SDG target 6.5. We have 38 institutions from 27 countries participating. You see the gray countries participating here, mainly in Eastern Europe and Central Asia. As part of this project, we had a look at the stable isotope analytical capacity in the project group. And as you can see here in the first chart is that countries with stable isotope analytical capacity were around 60% of our project group that is participating. Now I should say that we are representing, or we asked the counterparts and institutions that are working with us. So it could be that in given countries, there may be another lab that has the capacity, but overall, I would say this is quite accurate. And you can see here on the map, these are the countries that have stable isotope analytical capacity. And interesting to note, maybe despite the fact that almost half of them don't have isotope hydrology analytical capacity, it is interesting to know that almost in all sub-region there is. So that is an opportunity for sub-regional cooperation. as well as those only 5 institutions of this 40% have no experience in the use of these techniques, but others rely on external analysis or international cooperation. And out of the 60%, 12 institutions are regularly applying stable isotope techniques, including in national or international monitoring schemes, and 11 institutions conduct scientific research, regularly publish papers in isotope biology and other related applications. All counterparts, or almost all except for one, have a laser analysis, most of which actually are relatively young, and the annual sample throughput that they reported varies from 100 to up to 4,000 samples per year. The staff of these laboratories range from 1 to 7 people. And here in the bottom right, you see also the capacity to do, for example, tritium or carbon-14 dating, which is lower than stable isotope hydrology. So let's have a look at the tritium. So tritium is a rare and radioactive isotope of hydrogen. And the nucleus, as you can see here, of tritium contains 1 proton and 2 neutrons. And it is an important environmental tracer in isotope hydrology because it can help to understand the vulnerability of groundwater, and particularly shared groundwater resources, and thus understand the dynamics of groundwater and the groundwater surface interactions. And it can also help to constrain groundwater residence times and flow dynamics, as well as by improved determination of groundwater ages by the tritium and helium-3 dating method, for example. And as you can see here, so these gray countries are the countries that are participating, but around 60% of the labs do not have equipment or analytical tritium capacity, and around 30% of the lab have a tritium analytical capacity, but these 4 labs that you can see here in yellow and blue, they have no enrichment capacity, which is though needed, since the tritium in the water samples must be concentrated throughout the process of electrolytic enrichment to attain a measurable level by liquid scintillation counting. And the ones in blues have an enrichment possibilities. The one blue here in black is the isotope hydrology in our building here in Vienna. So around 10% of the entire project group have liquid scintillation counting and coupled with enrichment unit possibilities. We also asked our counterparts on isotope hydrology in the context of policy making. And there, actually, that responds to the capacity to use stable isotopes in these labs. It is not surprising that almost 70% actually answered that it is not used to formulate water policies in their countries, or only occasionally used in the context of case studies. And only 30% reported that it is either regularly done or often done in the context of case studies. And similarly, although 60% actually reported to have analytical capacity, 80%, almost 80% of the countries mentioned that there is no isotopes integrated into national monitoring in their countries. So this project therefore wants to dock into this, first of all, increase the awareness on the existence of isotopic techniques, because it's still something that has to further be done in the region, to transfer the knowledge and build capacity, and mainly through the answering of specific sub-regional and transboundary questions, to enhance and sustain regional monitoring network, and ultimately to produce results that lead to the policies and follow-up actions. And we mainly do this to case studies. And these case studies that you can see here were basically put together on mainly 2 criteria. Either they should be transboundary in nature, so for example, focusing on transboundary surface water or groundwater resources, or at least thematical, such as you can see here, for example, the one focusing on water resource degradation in coastal regions, or the nitrate case studies. You can see here the one, we have one on groundwater in karst aquifers that is transboundary in the Western Balkans, Bosnia and Herzegovina and Montenegro, as well as 2 rivers, the Sava River and the Sirdarya River. We will focus on vulnerability of deep and stratified aquifers, as well as on source, age, and recharge pattern of groundwater for irrigation, SARGE. And since we don't have time to go in all, I just want to quickly introduce you to SARGE, which is basically put together from Ukraine, Moldova, Romania, and Bulgaria. And the reason for that is that these countries are having a high per capita groundwater depletion exported. And there is relatively little information about the apportionment of irrigation water. So the proportions of surface water use versus groundwater abstraction. And hence, more information is needed in this area on the age, the timing, the mechanisms of groundwater recharge. And no sound scenarios of future water use have been established. So this study really aims to, first of all, determine the sources of irrigation water supply in these areas. Does it come from river water, young and old groundwaters in this area? Then to investigate the recharge patterns of young groundwaters and to determine the age of old groundwaters. And the isotopic compositions of both groundwater and precipitation in 4 large transboundary aquifers, 2 surface and 2 deep, will be investigated. And you can see them here on the map. One is stretching Romania, Moldova, Ukraine, and one between Romania and Bulgaria. And the groundwater will be sampled twice per year in spring and autumn. The collected data will be used to feed into a 3D groundwater flow path model. And then this is hoped to basically generate scientific evidence to develop a tool which may inform the improved management and usage of water in the region that is prone and will be prone to various climatic, environmental, and economic risks in the future, thus aimed at helping decision makers to adjust and adapt to existing irrigation practices. And here are just a few pictures. We have started with the sampling campaign. We have provided our counterparts and laboratories that we are working with sample equipment and consumables. We have been starting to conduct mainly virtual training courses because of the pandemic, but we have also started to facilitate exchange between the labs by, for example, supporting individual researchers to visit one lab to analyze samples there. This is, for example, the sampling that has taken place at the Oko case study in Bosnia, sampling in Czech Republic for the nitrate case study, and we are, of course, also through the submission of equipment and sample equipment to our counterparts. We are hoping to enhance our GNIP monitoring stations, which is the global network of isotopes in precipitation. This is a station, a new sampler that we installed in Montenegro, for example. These are us. We are happy to answer any questions. As I said, I'm presenting on part of this group, and I'm looking forward for answering any questions later. And thank you again for listening to my presentation.
Many thanks, Christoph, for this presentation. And personally, I find it very useful because this study and this actually, advocacy for the method, because isotopes are used already for quite some time. I remember when I started in the 80s, we used it in karst from Yugoslavia. But you mentioned some other very useful possible implementation related to pollution and related to agriculture and etc. So it's very useful. I also have some questions, but I will keep it for the end, and especially because there's another presentation coming on isotope as well, and by Oliver. Only it's the other region. It's not Europe and Central Asia. It's now we are moving to Africa, and I'm very curious to hear what would be specifics of implementing isotopes in Africa. And the title of your presentation is evaluating and developing regional capacities for isotope-based assessment of transboundary water resources in Sahel, Africa. Oliver, the floor is yours.
Yeah, thank you. I hope the sharing of the screen now works better. So, can you see my presentation screen? Great. So let's start. So yes, just to introduce myself, I'm Oliver Kracht, working in the isotope hydrology section of the International Atomic Energy Agency in Vienna. And right away, before talking about these developing regional capacities for transboundary assessment with isotopes in the Sahel region in Africa, I want to thank the team that is behind here. So I want to thank Mr. Barbico, Madame Skier, Mrs. Gossi, Mr. Hinault, Mrs. Trabelsi, Mr. Travi, Mr. Tsuari, and Mr. Niviaras and Luis Araguas. But that are the experts that helped us on an international basis in this project. But there's even more names behind, and it would be dozens and dozens. These are the names of the people working with us in the country, so which are actually the regional technical experts. And I don't have the time to name them all. So my thanks goes to all the countries that have been collaborating in this regional project with us. Okay, the IEA, you have already seen it from Christoph. So the first session we had this morning, the panel session, let's say, pointed out that for implementing what policymakers are envisioning or discussing or suggesting, in the end, we need data on the ground. And to obtain data on the ground, we need capacity on the ground. That means the member states, the local teams, the local experts need to be able to produce hydrological data, and in our case, to produce isotope data. So that's what I want to talk about today. That is how in the regional projects in the regional projects we conducted in Sahel Africa, we built up these capacities for isotope hydrology. So, and I'm actually talking about two projects, which has very boring numbers for us. IEA just gives numbers to projects. So it's Regional Africa 711, Regional Africa 1719. Two in a row, the first one starting in 2012. So the aim of this first project was to respond to the critical issues of adequate water resources management in the Sahel region, and supported a comprehensive approach to integrated sustainable groundwater management, bringing together a wide range of stakeholders and development partners, national governments, river basin authorities and local authorities in the region. So here you see the member states that have been participating, 12 member states, and we have covered or tried to cover, let's say, or make groupings within this team in 5 aquifer systems or basins. So that is not, there's no transboundary. It's sometimes it's more a system than an individual aquifer, but we had to find a systematic to group this effort. So we are speaking about the Lumitin aquifer system, the Liptako-Goma Upper Volta system, the Senegalo-Mauritanian basin, the Taureni basin, and the Lake Chad basin. And they are a bit better depicted here. So you see, let's say, a blend of, let's say, transboundary regions, but transboundary aquifer regions, but also the blend of where our teams have been working, starting in the 711 project. I hope you can see my slides changing, because on my computer they are not changing anymore. So
no, it's not changing in the moment. It's the map of Sahel.
So you don't see a slide that is called approach, but you see a slide that is called projects.
We still see the Sahel map, Oliver.
It's a Sahel. That one is
okay. Then
stuck.
I think the only possibility is that I stop sharing and start sharing again. So something seems to be on hold. So just a second, please.
I thought you want everyone to be sure to learn where Sahel is.
No,
so
sorry,
kept
it seems like I'm seeing my slides progressing, but
okay.
you didn't see them.
No.
So let's try again. I'm sorry.
Is he sharing now? You don't see anything now?
Just 1 second. I had to start the application again because it really stalled. I'm sorry. Just a second. So now you should be able to see my screen again. Can you confirm? And now you should see a new slide. Is it correct? Thank you, and I hope it remains. So here you see, let's say, a picture of how we distributed the different teams, the different member states teams in the different aquifer systems, and the regions where they have been working in the first project from 2012 on. I told this already, but my slide was the wrong one. I'm sorry. So now I hope the slide is changing. And you can see our approach that we took in the first project. So the idea was to assess the distribution of current tritium and stable isotope content in precipitation and rivers, identification of mapping areas of present-day replenishment of groundwater. So that was the two ideas. Contributions to the global network of isotopes in precipitation and rivers also. But also, let's say, some chemical questions like assess water quality in groundwater, salinity issues, natural versus man-made pollutants, nitrate, iron, fluoride are concerns in this region. The spatial distribution patterns, sources, and pathways of these pollutions. And to determine the interconnection between aquifers and surface water, so groundwater surface water interactions, and very important changes in the water balance, which is very important for transboundary policy making. Finally, to assess the sustainability and resilience of groundwater resources and water quality. So I hope the slide has changed. So we had a bit of different approaches in these different basins and in these different pilot study areas. Of course, determined by the needs and the problems, the water problems that are observed in the individual areas, but also determined by, let's say, the knowledge gaps that are there, which were quite different in different regions. And of course, also the hydrogeology, it's in the end not the same. So if you look at the pilot study area 1, which is the Senegal-Mauritanian basin, the issues addressed in the first project was the interconnection of deep and shallow aquifers. We took about 50 carbon-14 samples for the deep aquifers to estimate groundwater age, but also to estimate groundwater surface water actions and salinity issues in the coastal parts of these aquifers. And in the current project, the RAF 1719, we will continue on this, but we will put more focus on deep aquifers and also establish age traces like Krypton 81 that can reach back to even longer back in time. Also establishing noble gases for the deep aquifers, which also can give information about ages in, together with the krypton, of course, but also recharge conditions and recharge temperatures. In the Tuadini part of Algeria and Mauritania, unfortunately, no sampling was possible so far because of security issues in this region. So fieldwork is very difficult there. Whereas in the part 2B of this second group, in the southern sector, between Burkina Faso, Mali, and Mauritania, this is a region where very few information was available for isotope hydrology in the beginning. So our aim was kind of a reconnaissance of shallow aquifers, about their transit times, chemical parameters, nitrate pollution. And to our surprise, in especially this northern region, and I may use the pointer, maybe. So in this part of the study area, we found relevant recharge also in the aquifers from the tritium data, which was not expected. So that was quite a surprise in a yet data scarce region. This will continue in the current project, but also the focus will move a bit more to the deep aquifers. In the Liptako Goma Upper Volta Basin, so that is approximately here, shared by Burkina Faso, Mali, Niger, Ghana. If you put it a bit wider, let's say, the focus is on shallower aquifers in fractured granitic rocks. So we're looking at groundwater ages, but also at nitrate pollution, because this water is really used for drinking water purpose, but also, let's say, endangered by agricultural pollutants and domestic pollutants. So many tritium results also show active recharge in this area. And what is interesting here, we are now continuing with PhD work thesis. So after the first project, which was mainly done with established staff, we found that capacity building in the region would profit from having, let's say, young researchers at the beginning of their career being involved and having a career perspective to work on groundwaters in the region on a long-term basis. So you see this for many parts here now, that in the new project we have these PhD sandwich programs that build up on the first project data and now follow up a detailed research in terms of PhD programs. So in the Illumidine aquifer system, we have few samples also for security issues, but we can continue working in the northern sector of the Illumidine, which is served by Benin, Niger, Nigeria, and Togo parts, let's say, approximately here. We are mainly looking at groundwater surface water interactions, and not so much on the Niger itself, but on all the contributors of the Niger. And last but not least, we are looking at shallow aquifers in the Lake Chad Basin. So that's kind of a rough overview of the different, let's say, sub-projects that were conducted here. And you can see here the sampling areas from the first project that lasted until 2018. And you see, let's say, points where isotope samples and chemical samples have been taken for monitoring isotopic composition of precipitation, river water. Yeah. And you just see a few numbers. So we have more than 2,200 chemical analyses. We have more than 2,000 stable isotopes analysis, more than 1,400 tritium analysis. I think that is very beneficial for the region, in particular to delineate pollution issues for the shallow aquifers. But we are also addressing with more than 100 samples the deep aquifers and the older groundwaters. Okay, here you see just a map of the new project. So that is our aim, let's say, or our current work as a follow-up approach of the first project. Since 2018, we have a follow-up, and you see again, let's say, the sampling points that we are doing in the different countries, which is quite a very interesting coverage, I should say, for isotope hydrology. As I said, we also want to, let's say, enforce our GNIP and GNIR activities. So that is, let's say, monitoring isotopic baseline data in precipitation, but also in rivers. And so GNIP is the global network for isotopes in precipitation. GNIR is a global network for isotopes in rivers. And there are quite challenges in these regions. So you see a lot of points here, but the green ones are those that are active now, or better to say reactivated, because I would say for precipitation, what we see here, most of the green sites are reactivated because they had their good time in the 1970s, 80s, but then somehow many of these monitoring activities declined, and we have been able, and we hope, sustainable re-establish these activities to get these baseline data. And you see the same situation for the GNIR, which is still a bit in the beginning. So we have a few here, and many of those still needs to be discussed. One important thing on another page, let's say, but very much connected here, was the IWAVE projects that we undertook in the Sahel region. So IWAVE is the IEA Water Availability Enhancement Approach. And what does it mean? So it's kind of a approach And you see here highlighted the countries where we already did this, and we are continuing with the other member states in this project. So the idea is that after many of these collaboration projects in the past, we want to, let's say, better benefit from the synergies, but also from the holistic approaches in the region and with the member states, and to find out how isotope investigations can really target the, let's say, knowledge gaps that are there for the water stakeholders. So IWF consists of a, let's say, series of reportings that are jointly worked out by experts, by the agency with the help of international experts, but together with the member states. So it's kind of a 50 to 50% shared approach to identify knowledge gaps in national hydrological data and information, to, let's say, then distinguish the expertise and technology and the infrastructure that would support to address these issues, so the agency better knows where capacity building is needed to really answer the relevant water questions, and to then propose the isotope and nuclear techniques that are needed to fill these knowledge gaps in hydrological information. And also to promote collaborations within, let's say, transboundary systems between different member states, but also within the member states, so that the different national or international organizations can work together to identify these gaps. And to assist the water agency with scientific support and technical isotope services by the IEA, of course. And oops, I was too fast. So far, we have undertaken the IWF in Benin, Cameroon, Ghana, Mauritania, Niger, and Nigeria. And you just see two photos here. One is from Nigeria and one is from Ghana, from two of these workshops that we have undertaken. So we start this always as a desktop study, but then we meet with the water stakeholders in the country to join together to introduce high isotope hydrology also to those that have not yet been let's say, exposed to it, and to really find out in a collaborative basis in the countries, in a series of workshops, where are the opportunities where isotope hydrology can really help to answer water-related, let's say, data and information questions that have not yet been addressed. So one of the outcomes of this IWF process was to inform us where capacity building in terms of, let's say, laboratory capacities and hydrological capacities is needed. And so we identified, in the end, you can see just a number, quite a dozen of countries, 1 dozen of countries: Algeria, Benin, Burkina Faso, the Central African Republic, Ghana, Niger, Nigeria, Senegal, Togo, where we have helped our counterparts by equipping them with an isotope hydrology laboratory basic infrastructure by laser analyzers for the stable isotopes. 2 of them had already, Ghana and Algeria, isotope facilities from previous projects, so this was upgraded. But the others you see here, the other 10 you see here, have received new laser facilities and now are able to do their stable isotopes analysis themselves. For the bit more, let's say, advanced techniques, we were able to also help Algeria, for example, to upgrade their tritium laboratory with a new scintillation counter. But we also found that need is also not only for isotopics infrastructure, but many of the partners have difficulties or have in needs to also undertake the basic chemistry, so that this can be interpreted together with the isotope data, which is very much needed. So we have also supplied ion chromatography systems for 4 of these contributing countries to that they complement the isotope hydrology labs that have the lasers now. But I think that is in particular the laser analyzer, the advent of this technology, which is a bit easier to use than conventional mass spectrometry, really allowed us now to have a very significant numbers of local laboratories that are hopefully in the future are able to undertake their isotope analysis themselves. And I think that is really a progress that have been gained over, let's say, the decade of these 2 projects. Another outcome of this I-Wave approach and the considerations that were chosen, let's say, concluded from this is what I've mentioned already, is these PhD sandwich programs that we are following up in the current project in the 1719. So we have about now 16 PhD sandwich theses. And you see them here. So this is the opportunity from people from different member states in the region to go out to an international education and hopefully building capacity in the future. So, okay, thank you. That was my last slide. Thank you.
Many thanks, Oliver. It was a very inspiring presentation, and personally, I learned a lot about isotope implementation and in Sahel, and importance of the baseline. It's certainly something we should bear in mind. When I say baseline, that means, okay, what has been done, they're using these techniques, but also who are the possible partners, who are which institutions. And there's also something else, all these presentations so far were about cooperation and international cooperation. And what I see that we need to use outcomes of analysis like this to strengthen cooperation also among international organizations. What Atomic Agency can offer regarding isotope analysis, there are other UN or UN-related relationships which can offer in other expertise, put it together and join the forces. Many thanks. We will move further to another transboundary cooperation, but now other part of the world. We will have Moti. Moti, you are around? Yes, I see you. And it will be a presentation on transboundary aquifers between Nepal, India, and Bangladesh for SDGs. Moti, the floor is yours.
Thank you very much, Director EGRAT Center. So can you hear me? Hello?
Yes, we can hear you, and we are just, oh, great. Now we see a presentation coming.
Yeah. Okay, so I was listening previous presentation, and it's good to know that there are very interesting work already to understand the transboundary aquifer system. But in our region, but in our region, groundwater is regarded as easily available resources, and much focus is on its use and exploitation rather than focusing on its sustainable use and understanding the whole aquifer system. So what I'm trying to do with this presentation is giving the overview about the importance of our transboundary aquifer system situated between Nepal, India, and Bangladesh, and their link with SDGs. So this is Moti Lal Rijal. So I am a faculty in Tribhuvan University, Kathmandu, Nepal, at Central Department of Geology, and just I put the framework of my presentation, highlighting some background and water resources in this region, groundwater and sustainable development goal for this particular region as a regional perspective, and then aquifer setting, transboundary aquifers, role of TBAs in the region, TBA and SDGs, management of TBAs, and way forward. Just I will give a presentation on this. So just highlighting the geographical setting of Nepal and India and Bangladesh. So we are so Nepal is situated at the northern part, and most of the rivers in Nepal are originated starting from some of the river from also from source area also includes Tibetan region, and some also include Bhutan. So we have river basin that's share between India, Nepal, and finally all rivers goes to Ganga, and then these all rivers go to Bay of Bengal. So just and Nepal situated at the headwater. So we have from east to west, we have three major river system, and our most of the river system are transboundary river system. The hydrological dynamics in this region is quite unique. So we have very strong summer monsoon dominated hydrological cycle that includes 80 to 90% of precipitation happens within 100 days of summer monsoon period, and high seasonal variation of surface water sources. So we have the problem of too much water during monsoon and very little water in the season after summer monsoon. So we have the long seasonal gap of precipitation because we have this relatively weak winter monsoon and then very strong summer monsoon at the 80 to 90% I already indicated. So this kind of hydrological cycle in this region brings very huge flooding, and we have very long gap of precipitation. So we have also happening frequent drought. And another problem is our surface water is also very much polluted with physical, chemical, and biological contaminant. So just highlighting this groundwater in Nepal. So we have groundwater system in hard rock aquifer system, where in the yellowish and this southern part, which is shown with yellowish color and white color. So these are the groundwater system, mostly dominated area, and it has this aquifer system, mostly shallow aquifer, is very highly used, 50 to 60 meter deep, from 50 to 60 meter deep well, and then this deep aquifer system is also utilized heavily. So looking at this, okay. So just giving this is the overview from south to north cross section area of Nepal. So what I want to show with this cross section is this: in the southern part, this Tarai area and Dun Valley area, we have strong aquifer dominated system, where in the other high altitude area we have strong spring systems are there. So groundwater are available in the form of spring in the hills and mountain, whereas in the lower altitude in the Tarai area we have very rich groundwater resources in the form of different type of aquifer. So just giving the overview of now what groundwater means in this region. So we have very strong groundwater dependent irrigation system in Nepal, 70%, India around 60%, and Bangladesh 79%. All irrigated irrigation is depend on groundwater dependent irrigation system, and groundwater, as I also mentioned already, because surface water is highly polluted in many areas. So mostly drinking water is mainly groundwater only. And we have also the hydropower system in non-snow-fed watershed. This hydropower system are also contributed by hard rock aquifer and castified aquifer system in hills and mountains. And also for water for industrial and ecosystem and environment, because Himalaya region is the hot biodiversity hotspot. So this is also a groundwater system, and groundwater dependent ecosystem are very dominant in this region. So that means the importance of groundwater is very high, and our agriculture, our agro ecosystem, and our drinking water, water for hydropower as well as industry, all mainly related with the use of groundwater system. So that means pressure on groundwater system, whether we are getting groundwater in the form of spring in hills and mountains, and also by pumping of shallow and deep aquifer system in Tarai, southern part. So all of these systems are mostly utilize groundwater. So just this is the this transboundary aquifer system. Mostly just took reference from this IGRAC website. So we have in this region we have two dominant transboundary aquifer system: this AS79 and AS80. So that includes 3 countries: Nepal, India, and Bangladesh. And in this transboundary aquifer system, you can see that this Nepal is in the northern part, so that all the rivers and that's flowing from Nepal, and they originated mainly from Nepal, and also from part of Tibet, and also some of the river basin we share with India, and also we have the common river basin, river source area coming from Tibetan region, and also we share this basin with Bangladesh. So that means this transboundary aquifer area that's indicated with yellowish color inside Nepal. So these are, we call this as a food basket area. That means our whole agriculture and major settlement all lies in this part of the region. So agriculture dependent, this irrigation and also the drinking water for this municipal supply, and drinking water for agro ecosystem, and also for environmental flow. These all are maintained by this shear aquifer system. So just coming to how we can, in this region, groundwater resources and SDG, if we look at the 17 UN SDGs, and out of 17 SDGs, so this no poverty, this SDG to zero hunger, good health and well-being, clean water and sanitation, affordable and clean energy, and SDG 8, decent work and economic growth, sustainable cities and communities, this SDG 11, and climate action, SDG 13, life on land 15, and also the 17, partnership for the goal. So these all SDGs are directly and indirectly related with the groundwater resources, because this poverty alleviation mostly linked with agriculture dependent this GDPs, and this is mostly farmers dependent economy, and then also zero hunger, because we need to increase the irrigation potential, irrigation fed by groundwater. So this will also help to reduce this hunger, and also the good health and well-being, because we have many waterborne diseases related with the drinking water, and this has also well connected with the availability of the drinking water from groundwater resources. And of course, this SDG 6 directly related to clean water and sanitation, mostly supplied by the groundwater in this region. So, and this affordable and clean energy, many solar power pumps are now being used to pump groundwater and to help smallholder farmers. So this also has a very important role, and also the decent economic growth, because we have the agriculture dependent economic growth in these 3 countries, and we have the sustainable cities and communities. So we have this increasing urban area that's mostly also dependent with the groundwater, and also for this in this urban industries. And of course, this climate action we can build by managing transboundary aquifer in this region. We can also by using climate action and this for the sustainability of the aquifer system, we can also link this climate action, because we have this natural based solution and this climate change resilience building by managing aquifer recharge and this system, because we have too much water and too little water problem. But by managing our this transboundary aquifer, we can implement climate action and of this SDG 6, and also life on land, as I also mentioned in my previous slide, because all agro biodiversity and then this environmental flow and ecosystem sustainability also depend on available of the groundwater resources, whether groundwater available in the form of spring or groundwater available by pumping from aquifer system. And then partnership for the goal, that means by partnership with the neighboring country who have shared this aquifer systems, transparent aquifer system, we can set the new goal and build a strong partnership utilizing this SDG part. So this just the I think that's just the standard logos. I already discuss link, direct and indirect link of these SDGs with the groundwater system in this region. And as I already mentioned, because our aquifer system in our region are very much less focused, and their sustainability also very less discussed, because many transboundary rivers, when we discuss on water resources, then mostly we discuss the transboundary river system, not transboundary aquifer system. So now I think it's time to look further integration of aquifer system and transboundary aquifer system in transboundary. Why we discuss about the transboundary rivers? So because Nepal is situated at the mostly at the recharge area, because we have the lateral recharge as well as vertical recharge of this transboundary aquifer system AS79 and AS80, which I have shown in the previous map. So therefore, utilization of natural hydrogeological setting, that means science-based or hydrogeological science-based planning and management of TBA is very important in this particular region, and we have a very well delineated recharge zone, and this we can manage this kind of recharge zone, and also we can intervene in this recharge zone to enhance recharge of surface water, which is available only in monsoon season. We can manage in a way that we can use nature-based solutions. So that means what I want to say with nature-based solution means we have very well delineated recharge area, and then we have the detailed map, and we can intervene in the system. Then we this seasonal available flood water we can manage in a such a way that it can recharge groundwater system of the region, utilizing this nature-based solution, building dams or increasing the residence time of flood water by by green river corridor development or systematic bio dams. And another thing is disaster risk reduction can be also incorporate to manage TBA because of this high flood and high flood water. We can also control by utilizing this recharge or increasing the fractionation of surface water to groundwater system. And then other one is building climate change resilience, because too much water and too little water, or climate change means change in water. So in change in water means surface water is very dynamic in our region, but groundwater accessibility and availability we can increase so that these smallholder farmers and can also use this clean energy system or solar power pump by increased surface water and groundwater recharge, making surface water more favorable to recharge groundwater in the region. So this all I included in the management of transmountain aquifer system in the region, because in the area we have very strong lateral recharge and in the southern part, and it goes to less recharge and less recharge when you move towards from northern part to southern part. That means just crossing the border after Nepal, more abstraction of groundwater is increasing in the southern part, whereas recharge of the groundwater is more at the northern part. That means this management, I think we need to focus from recharge zone to from recharge zone to abstraction zone, and I think this kind of a holistic approach from starting from recharge zone to abstraction zone can lead to longer sustainability of the TBA, because we just have this general or regional map of TBA, but the detail our aquifer system in this AS79 and AS80 is less understood. So what we need to do further is share groundwater resources. That means addition of aquifer system in transboundary river system. That means rivers, transboundary river system, we discuss a lot, and we have some kind of understanding to governance of this kind of share river basin, but we do not have any better understanding or the local high resolution map of this transboundary aquifer, because it's a general map AS79 and AS80, but we need to look further understanding of this TBA, because in some area already we have seen very high depletion of groundwater level, and other area is not much depleting. So that means recharge dynamics also different, and abstraction is also very high and very focused in some areas. So that means this boundary condition and recharge dynamics and abstraction amount of this in different region of this shear aquifer system, this AS79 and AS80 is not well focused. So we need to differentiate this aquifer system into subsystems so that long-term sustainability and sustainable use of groundwater in the shear aquifer system can be better understood. And this understanding of the TBA is important, and then management of TBA, of course, it comes more on the also the governance part, and also TBA, a component of regional cooperation, because we have the South Asian regional cooperation in this in 7 countries, and then Nepal, India, Bangladesh also a member of this SAARC country region. So in this SAARC country regional cooperation framework, I think this transboundary aquifer system can be discussed, and the formulating of kind of policy, government, or plan to monitor and to govern this kind of shared aquifer system would be quite beneficial to understand and long-term sustainability of this aquifer system. And another point, achieving climate change resilience through management of this transboundary aquifer system. So that means we have too much water in monsoon season, and then very and long-term drought and less water in this winter season. So by managing this transboundary aquifer system that we share with Nepal, India, and Bangladesh, from recharge zone to abstraction area, I think we can move towards long-term sustainability of groundwater resource system in this region, because our all agriculture, I already mentioned, our whole this agro biodiversity, this GDP three country GDP also agriculture dependent economic we have, and we have the many small holder and farmers are there. So that means if groundwater is not available, then our whole this system I think going to face great challenge in this context of climate change, and definitely it would all help us to achieve our sustainable goal in this region, because as I mentioned earlier, this 10 goal out of 17 are directly or indirectly related with groundwater system. So I think with this, if you have any comment, suggestion.
Many thanks, Moti. Many thanks for this very thorough presentation and putting this very important aquifer on spot. You mentioned the importance of regional organization, regional cooperation, and next presentation will be on the role of regional communities in transboundary groundwater cooperation by Jacques. Jacques, I understood that there is a video, but Jacques is also here with us to answer possible questions. Hi, Jacques. So could you start video, please?
Good morning, everyone. Good afternoon or good evening, whatever you are. I'm Jacques Ganoulis from Thessaloniki, Greece, and I'm sitting here in order to present to you, without waiting, the following presentation about the role of regional communities in transboundary groundwater cooperation. This is a joint presentation with my friend John Fried from the USA, the University of Irvine at California, and Haralambos Koulikais, who is active in Aristotle University at UNESCO chair. And this is about two case studies which are in a way opposite. The first one is a successful case study, which is a local agreement between the canton of Geneva, Switzerland, and the Department of Haute-Savoie in France. This is a local agreement, not between the governments. And the second negative case study is about the Greek and the Bulgarian government, who started drafting a kind of early warning flood system at the river of Maricha, Evros. At this river, there are frequent floods and catastrophic consequences. So it was important to develop an early warning flood system. And at every scale, local, regional, or national, there are groups of stakeholders competing for their interests, as shown at this slide. You have scientists, public, knowledge generators. You have the professionals, the politicians, of course, which are responsible for policy implementation, and also the civil society, NGOs. So all these stakeholders are active at local, regional, and national level, competing, of course. There are many conflicts between them. And at local level, they can draft and sign cooperation agreements, cultural activities. At the regional level also, you can develop some common monitoring, exchange of data. More difficult is the agreements at the national level, because to develop convention and treaties with parliamentary discussions is not easy. So the successful local agreement can be explained because these local groups have many other interests to cooperate, for example, tourism, transportation, exchange of goods, agriculture. So they have agreed to pay the cost for an artificial recharge scheme at this Genovese aquifer, and of course they share also the benefits. At the other case study between Bulgaria and Greece, these regional groups, authorities, public and NGOs, feel that they are oppressed by national administrations, so they are reluctant to agree through the ministries. They prefer to have local contacts. So with this, I think we can learn some lessons in order to start fruitful discussion, and I hope we will have the time to do this later on. Thank you very much for listening. Thank you.
Excellent. You see that in several minutes, the very clear message can be shared. We not having much time left, so if you don't mind, Mr. I would like to move to
I'm not yet made
next
presentation,
presentation, and that's the last presentation.
Yeah.
Okay. Yeah. And that. Okay. Okay. And that will be Susilavati from Timor, Indonesia, telling us about transboundary aquifer management on this island. And I understood there is a video. So could we see the video, please? Thank you. And I see Susi there.
Good luck to all of us. I will present to my paper, Transboundary Aquifer Management on the Island of Timor, Indonesia. This outline of my presentation. The background, this island of Timor, this the Timor-Leste, and this part, a small part, and this one is part of Indonesia. The hydrology of Timor Islands this aquifer in this place. This one, yeah, and Timor also record in transboundary world map, and I will explain integrated water resource management concept like this, yeah? And the lesson learned from the several countries concerned in special edition of the Journal of Hydrology. There's some important point can be found like this, and the global issues like this, and the method. This data and analysis. This TBS and KRI Indonesia and Timor-Leste. This one, this aquifer, this the border, and also this the border, a small part, this aquifer also. So 3 aquifer. This 9 district of Indonesia, this concern of the transboundary aquifer, this, and also this 3 district of Timor-Leste is Bobonaro, Kovalima, and this one Oikusi. This one. This some fact, custom, and culture of the border population of the 2 countries are one and similar. The kinship story of the Oepoli is some here. Oepoli population comes from Oikusi. It is said that its origin comes from Oikusi, while Oepoli is a place for herding and farming. Likewise, the border between West and East Timor is the same language, Tetun language. This so far, no policy regarding transboundary aquifer has been found in Indonesia. Some of the problems that arise are the existence of a number of fields of agriculture land that are contested between the 2 countries. This in here in this one, But the communities who have difficulty accessing cities are a challenge for the government to facilitate and provide adequate transportation so that community access become easy, improving people's welfare. In fact, people are more obedient and afraid of customary rules than government regulation. Customer sanctions are very heavy. In addition to material sanctions, are also social sanctions where a person can be excluded from the community. Therefore, an approach through indigenous peoples and understanding customary rules to implement burden aquifer policies is more appropriate and can be applied sustainably. This the TPS concept I try to illustrate. Yeah, that's economic development support by adequate transportation infrastructure facilities. There's a local community approach and understanding of customary rules, and then will be such sustainable for this discussion. Yeah, government product balancing. There's input, there's the process, and there's the output will be transboundary aquifer management policy. And TBS management in Timor, water resource, water for life, this one will be motto for this. Based on the concept of integrated water resource management that has been agreed to international, it can be concluded that the management of transboundary aquifers in Timor Island, especially in the border areas, needs special attention in order to realize the SDGs, especially to streamline groundwater as an enabler for achieving the water-related SDGs. Thank you. So,
Great. Many thanks, Susie, and it was very educational for me. Jacques was talking about importance of local agreements, and you actually came now with a local community approach and importance of customary rules. And I think that these two messages actually are strengthening each other and very important. We are running out of time. Many thanks to all presenters and all participants in the session. And I give floor to my colleague, Paulina, to close the session.
Thank you very much, Mr. Kukurich, for having being here with us in this session. So thank you very much to all the speakers for these very interesting presentations. Thank you for the all the participants, also very numerous. And thank you for the interpreters and the technical team. And we are looking forward to see you in the next panel, which is panel number 3 on science policy interface in the transboundary aquifers context, which will take place at 1:30 p.m. And also, of course, later on at 2 p.m. in the session number 5, which is the science policy interface of transboundary aquifers, the role of science in the management of transboundary aquifers. Thank you very much and see you soon.
Okay. Good.